So given any triangle, if we draw the three angle bisectors, we know they're gonna meet at a point called the incenter I. And in the past couple of weeks, we have talked about how to calculate the length of AD, right? This is the angle bisector. What's the length of it? We talked about it. So now today we're going to talk about how to calculate like segments such as AI, this one, and then ID, for example, this one. We want to calculate these two segments, for example, right? Given triangle ABC, if I know the three sides, all right, now there's a lot of marks and formulas. Looks a little bit complicated. Let's go one by one. All right, let's try here with a brand new graph built from scratch. So three angle bisectors. All right, A, B, and C, and I. Now let's call this point D. Let's call this point E and F. I am more concerned about the line of AD, right? If you can calculate AD, AI and ID, then for BI, IE, and CI and FI, it's the same idea, right? It'll be very similar. Okay, so let's focus on this one. So AD squared equals, remember the formula? It equals AB times AC minus BD times CD, right? So this is C, right? AB is C, and then AC is B. So it's BC minus BD times CD, right? Okay, so what's BD and CD? So this is A, right? BC is A. A was cut into angle bisector ratio, right? B plus C. Cut into these two portions, and I'm taking the C portion here, right? BD is AC divides B plus C, think about it. And then similarly, CD, it was like A cut by portions of B plus C. And this time I'm taking this side, the right-hand side, the B side, I'm taking the B portion here. So that's CD. All right, let's put it back here. So it equals BC minus BD times CD, which is B squared, A squared, sorry, A squared, BC, B plus C squared, right? And let's try to simplify it a bit. So AD equals square root of BC times B plus C, and then B plus C squared minus A squared. Right, you can leave it like that. I don't want you to remember this formula. You don't need to remember this formula, all right? But we can derive it, right? On the run. Now, how do we figure this one out? And then eventually this one. One way to go is to say, okay, this is an angle bisector. So within triangle ABD, I can apply the angle bisector theorem. I know what's AD. And then AD was cut into two portions. But then AI over ID equals AB over BD, which, you know, we could write out the ratio. So let's try that. So AI over ID equals this divides BD, right? BD is AC divides B plus C. Cancel the C, that equals B plus C divides A. I want you to pay some attention here. This is a very nice ratio, isn't it? B plus C divides A. That is AI over ID. This over this is the sum of these two legs divides A. Very nice, no? So AI equals AD times what? B plus C divides A plus B plus C. right? You can think of that AD was cut into portions of these two parts, right? A plus B plus C, and I'm taking the B plus C part, right? Okay, so AI equal AD. AD is this, no? Square root of BC, B plus C times square root of B plus C square minus A square times this. B plus C divides A plus B plus C. Now, this is canceled, right? So we can write it as square root of BC, sorry. Square root of BC divides A plus B plus C times a square root of B plus C square minus A square. Now, we could take a further step because you realize this is a difference of squares, right? And then you will get a term of square root of A plus B plus C, right? Which sort of cancels part of the denominator here. So let's try that. So you will get a square root of A plus B plus C, square root of BC, and then what's going to left on top? B plus C minus A, right? If you are familiar with the syntax of writing a semi-parameter of a triangle, S is defined as A plus B plus C divided by 2, right? The Heron's formula, which we use to calculate the area of a triangle, then half of the parameter is defined as S equal A plus B plus C divided by 2. And so this could be further written, expressed using S. Why? It's eventually square root of BC divides square root of, there's 2S here, so I'm just going to write this, and then this one is what? 2 times S minus A. So the 2 will be canceled. So eventually you can write BC times S minus A divides S. I don't want you to remember this formula, but I want you to sort of remember this. And you understand how we get here, right? The calculation like this is important, especially eventually when you get into AMY, because all the problems are based on calculations, right? We need to be able to calculate, and we want to be able to calculate all these segments. All right, now to calculate ID, it's a piece of cake now, right? ID, think about the AD again. It was AD cut into 2 parts. And this time I'm taking the A part. All right, so you plug in this formula. B plus C square minus A square times A divides A plus B plus C. All right, a little bit messy, but again, we could further simplify if we use the syntax of S. You can see that this is the difference of squares, then there's gonna be like a square root of A plus B plus C, right? You could cancel potentially part of the denominator here, but you know, if you don't bother, we can leave it like this for now. And we don't need to remember all these formulas, but what's more important is that you being able to derive on the run, right? It's nothing too difficult, right? All right, now there is a interesting special case, right? So let's look at a little special case here. For example, if I tell you that B plus C equal to A. So basically I'm saying that the triangle 3 sides form a arithmetic sequence. Right, so this is B and C, this is A, and then B plus C equal to A. If that happens, interesting. So suppose this is the angle bisector from A, all right, and this is the incenter, I. Now, this is D, okay, AI, ID. AI over ID equal what? Remember, this is always true. This is always true for any triangle. But then B plus C equals 2A. No, this is equals 2. So it's like a 2-to-1 ratio. Right? So it's like AI equal 2/3 of AD then. No? Right? And what is AD? Well, we could take a look at our little formula here. AD is this, right? This is AD. And then this time B plus C equals 2A. So it's like square root of BC, this is 2A, this is like 3A squared. Right? So we got 3 BC square root divides 2. Right? Simplified, very simple right now. So that's something maybe we can remember. Okay, so for example, you can derive these formulas. Right, AD is very easy to derive now. And then AI is 2/3 of AD, and ID is 1/3 of AD. All right, how about we put in action and try to solve a problem? Something like this. 2012, AMC 12, problem number 18, triangle ABC. Okay, let's draw it. (27), 26, 25. I is the incenter. I is the intersection of internal angle bisectors, right? What is BI? Sounds like something that we have just learned. Now you can start doing a lot of different things, but one thing interesting is that not only they're telling us the 3 sides, but the 3 sides do form a arithmetic sequence, right? 25, 26, 27, and 26 is the middle one. So right now I do have like A plus C equal to B, and I'm looking for BI. Which formula am I supposed to use? Well, if you don't remember the formula, that's perfectly fine. What we're gonna do, let's just say this reach AC at point D, all right? Okay, now I need to find out AD and CD, right? So it's like 26 divides, that was 52 times 27, and 26 divides 52 times 25. So this is 27 over 2, this is 25 over 2. So AD and CD, very simple numbers. And then what's going to happen next? AD is square root 27 times 25 minus 27 divides 2 times 25 divides 2. That's AD, right? But then BD, here, BD, right, coming from B, okay? And then BI is basically 2/3 of it, right? We learned that. Right, let's try that. Take the 25 out. Right, so 10, 3, 2, 9, 15. We're gonna go with this. All right, now I have just showed you on the run, how do we solve a problem like this? I did not directly use a formula like this. I assume many of us may not remember this, but what's critical here is that you remember these formulas, these three. All right, it's very nice and very simple to remember, and especially it's very helpful if we have an arithmetic sequence condition, right? Because this becomes 2. One of these will become 2. All right. Now, there is another way to solve this type of problems. And I think it's important to introduce that. Think about this. I want to calculate the length of AI, knowing that I is the center of the incircle, right? Incircle, the circle that's tangent to the 3 sides of the triangle. Now, this is a right triangle, no? ID is the radius, the in radius, the radius of the incircle. AD, do you know how to calculate AD? AD is S minus A. All right, this is a very well-known basic result. AD equal S minus A. Now, what about R? How do we calculate R? R, we're gonna use the Heron's formula. S times R is the triangle's area, right? But the triangle's area also equals S minus A, S minus B, S minus C, right? This is a very well-known Heron's formula. So, okay, R equals square root S minus A, S minus B, S minus C divides S, right? S is the half parameter, okay, semi-parameter. So basically, if I tell you the ABC, the 3 sides, you can calculate the in radius, not a problem. So, all right, so that's R. And AD is S minus A. So Pythagorean, right? Pythagorean inside this right triangle. AI square is AD square plus R square. All right, let's try that. R square is S minus A, S minus B, S minus C, plus AD square, S minus A square. See a common term of S minus A, so let's take that out. S minus B, S minus C, plus S minus A times S, right? Let's try to simplify this term, okay? Very interesting. This particular term looks very little bit messy, but let's try to see what it really is. S squared minus BS minus CS plus BC plus another S squared, so 2S squared minus AS. So it's 2S squared minus A plus B plus C times S plus BC. And that is exactly 2S, no? So this and this cancels. It turns out it's just only BC left. All right, very nice. So it's S minus A times BC divides S, the denominator. Okay, and well, we have just calculated the AI square using a completely different method. Does it match what we got before? This is S minus A divides S times BC. Well, what we got before, what did we get? Right here, right? BC times S minus A divides S. Perfectly match. Right? So now, potentially, this same problem, we could think again, if you do not use the angle bisector length formula, what are you going to do? Again, let's try that. So this is 27, 25, 26 incenter right here. I want to calculate this. All right. Well, this time you're going to draw in circle, right? Sorry for my terrible drawing, but now I can draw the radius. So right now I say I'm going to have to figure out this segment and then the radius. Now this is S minus B, right? What's S? S equal 27 plus 26 plus 25 divides 2. Right? So it's 26 times 3 divides 2, which equals 39. And let's call this point D. BD equal S minus B. That's B, so it equals 13. The radius, we're going to use Heron's formula. Right? S minus A, S minus B, S minus C divides S. That's all. All right, what did that equal to? 39 minus this, 39 minus this, 39 minus, so it's going to go up like one at a time, right? And divides 39. Two square root of 14. That's all. All right, so BI square equal 169 plus R square, right? 4 times 14, 56. Very nice, 225. BI equal 15. All right, completely different idea, but nevertheless, we get the job done. Now, which method is better? I say they are equally important. Both methods involves some of the fundamentals that you should understand very well. All right, both methods are important. All right, that's it for today. I'll see you next time.